Bueno, ahora sí vamos a dar comienzo a la presentación. Darle la bienvenida a todos los que se están integrando. Mi nombre es Cristóbal Oviedo. Estoy aquí junto al equipo de PES, lo que sería el capítulo técnico estudiantil de la IEEE de la Universidad de Chile. Tengo el agrado aquí de presentar al doctor Youssef Pipel Sadeh, quien nos va a dar esta magnífica charla, ¿ya? En un momento vamos a empezar con la charla, ¿ya? Y vamos a presentar primero que nada el doctor Youssef Pipelsadeh, es el director de operaciones europeas de Manitoba Hydro International. Él se unió a esta empresa, ¿cierto?, en 2016 y es responsable como director de operaciones comerciales para la región del Reino Unido y Europa, ¿ya? En 2012 completó su doctorado en sistemas de potencia en el Imperial College, publicando más de 10 artículos de primer nivel y galardonado con beca de investigación hasta 2015. Durante ese tiempo fue consultor principal en numerosos proyectos a través de Imperial Consultants. Es reconocido y nominado por el British Standard Institute como experto del Reino Unido y es miembro activo de CENELEC. Es miembro experto de IEC y hasta la fecha ha publicado numerosos informes técnicos, más de 25 publicaciones en la IEEE, IET y SIGRE, y ha contribuido a diversos estándares europeos. Entonces, ahora le vamos a dar paso al doctor, ¿cierto? Youssef, are you there?
Yes, I am here.
Yeah. Now you can start the presentation.
Thank you so much for the kind introduction. Hello and good afternoon, everyone. I would like to begin by thanking everyone for their time for today. Today's presentation is about large-scale electromagnetic transient model development for renewable grid integration. And specifically, we will look at conditions of power grids what happens when renewable grids, renewable energy sources face weak grid conditions. I would like to begin my presentation by highlighting a slide that was provided to us at Manitoba Hydro by AMO in Australia. AMO is the very important player for the electricity market. So the reason I would like to touch upon this is really, if we observe here, here it shows three different measurements. The first measurement in yellow, the dotted one, is showing what was the field measurements seen in the Australian network. The dotted yellow, I appreciate the colors are very similar. Then the same, this was a fault scenario in 2016 where Australia went through a blackout. If you look at the orange trace, we will see the performance of PSSE, and then the darker brown is more PSCAD. What we see up until this point, actually RMS or PSSE tools can do an exceptionally good job in looking at the system behavior. But what happens is when the system goes through very weak grid conditions, or let's say multiple contingencies where the connection of the grid is very weak, then you can start seeing that RMS tools can no longer correctly predict the response of the system. And that's one of the key reasons why in Australia, they have put a mandate to perform all their modeling in EMT. So those of you who follow the Australian power system world, you'll see that there is a lot of, there's a very hot, in the last couple of years, they have had a lot of interest in such studies. You can see in PSCAD, the yellow and the brown are very well matched. So that this is one of the drivers. In today's presentation, we're going to delve into three main parts. The first part is looking at providing you a general introduction to EMT and highlighting just the high-level basics. Then we will talk about the differences between phaser domain, in other words, RMS tools, and electromagnetic transient. We will also look at the impact of transmission network characteristics and network transients. I will highlight quickly what we mean by this. Then I will discuss inverters connected to weak grid locations. What do we mean by weak grids? I will discuss first what are our understandings of weak grid, and then what happens when you connect weak grids to the system. And then at the end of part one, we will look at some studies, high-level studies. Again, this will be pulled into part two. So part one is just a high-level introduction, getting you into the world of EMT. Then part two, I will discuss wide area EMT models. Are they actually necessary? Based on 4 or 5 examples, a couple of examples that we have performed in the past years, I will discuss some practical cases where EMT models are necessary. And at part 3 of the presentation, we will look at wide area, in other words, utility scale, large scale EMT model development, how to validate them, and more importantly, quite importantly, how to maintain them as we go along. Within here, I will illustrate one of our past projects, a large-scale EMT model development of the United Kingdom. Here, this is a system that comprises around 25,000 buses. We will show how this was developed in PSCAD. We will show an illustration of a part of the Chile grid power system. And to end the presentation, we will go through some demonstration on how to import Power Factory projects and PSSE into PSCAD. So system planners, operation, and transmission owners generally perform system studies in RMS tools. They typically perform load flow transient stability, whereby we're looking at the electromechanical oscillations, such as 0.2 to 2 Hertz, and they perform small signal analysis, eigenvalue analysis, whereby they linearize the power system at a particular operating point. They perform fault levels and typically harmonics. These are generally the tools that these are studies that can be performed in RMS tools. However, electromagnetic transients allows you to perform very fast transients. It looks at extreme high frequencies, known as ultra high frequency, and all the way down to as low as electromechanical modes. You can carry out all the above studies. We don't generally recommend it because it takes longer to perform these type of studies in PSCAD than it would with RMS tools, but it's something that can be done. So for those of you who've never seen PSCAD before, at the front end, you have the user interface. I apologize, this is from 4.6. This is the older version. We have now version 5 released, which is a major enhancement on version 4.6. However, just to illustrate the idea, the user would build their circuits by drag and dropping components on the graphical user interface. They would then specify what measurements they want to plot. They would press the run button, and then they can see waveforms. That's the front end of PSCAD, which is what the user interfaces with. At the back end of the PSCAD, we have what we call EMTDC. That converts these these elements into differential equations and then solves it. This is pretty much what I've just mentioned. So at the highest level, I would like to ask you to think about this question. What is a pure electromagnetic transient? So an electromagnetic transient occurs. So in order to get oscillations or electromagnetic transients, you need to have L's and C's in the network, okay? When you have L's and C's in the network, you have a pure electromagnetic transient. Now, in steady state, when everything is operational and fine, the waveforms, you see a three-phase perfect sinusoidal wave. Now, how do you get these high frequency components superimposed on your fundamental? It's when any of the following can happen. If you have a switching event, if you have faults in your system, lightning or any other events, which means that your topology of your system is now changed, such as this. For example, if you take this consideration, you have a capacitor inductor, you have two arms. If you suddenly open the close this breaker, whereby you're now initiating an energy exchange between L and C, what you'll see is high frequency components in your transients. Okay, so that's at the highest level. Electromagnetic transient is simply the energy exchange between LCs, and you can see that in the system. Now, why do we get damping? Damping is a cause of resistance. Resistance comes in many forms, such as loads, losses in transmission lines, and etc. Now, I'm moving on to just discussing fundamentally what is the difference between RMS and EMT in terms of mathematics. I won't dwell too much on this, but just to illustrate, when we're solving a load flow or transient stability or a phasor domain, we are solving the equations at one specific frequency, 50 hertz or 60 hertz, okay? Now, for RMS, this allows you to perform studies which are good for, 50 hertz solutions. You can perform, it's very good for electromechanical oscillations. However, they're not very good for representation of power, PV and solar when the system is weak. And it cannot represent systems which have resonances. In electromagnetic transients, we are solving the differential equations, whereby we are solving point by point by point on the waveform, and it's independent of on a single frequency. So essentially, we're able to obtain the range of harmonics that you see in the system. This is not a good illustration of range, but I will explain that later on. So the network characteristics of your system from 0 hertz all the way to several thousand hertz can be represented simply because we are solving the differential equations. One other important factor where EMT solvers can benefit, well, I shouldn't say benefit. One other reason is point-on wave. A simple illustration of a point-on wave is shown here. What is a point-on wave? So a lot of utilities and engineers typically for specific studies such as transient recovery voltage, TRV, TOV, switching studies, have to perform a range of sensitivity analysis in order to find out what is the worst operating condition for the study. So what they do is perform a point-on wave study. Now, when you're performing a study, the breaker logic does not get closed at any moment. It can actually close at any moment along the cycle. So depending on where in the cycle you are closing the breaker, you may have a higher your network will experience different transients. So point-on wave is an extremely important study for under certain situations. Another very important reason why EMT is important is when you look into the network, okay, let's say you have a very simple system comprised of two parts like this. And when you interrupt the circuit by opening the breaker, and then when you look into the system, okay, what you'll find is that there is a resonant point, a parallel resonant point. In this case, there's a parallel resonance at frequency of 600. So there's 12th harmonic, okay? Just after the 12th harmonic, we have a parallel resonance. Now, if you trip the circuit, what you'll see is that this 12th harmonic will be sort of shown in the transients, okay? Now, take the assumption where you are trying to connect the wind farm or any power electronic device to your system, okay? If that power electronic device injects or takes in, feeds in 12, or the controls of the wind farm have can take in 12th order harmonic, it can cause to amplify the resonance and cause major problems. Okay, so network resonance is extremely important. Network characteristics are extremely important because they can cause many problems to your inverters. I will spend a few minutes discussing some examples of what RMS, when we compare RMS with PSCAT, EMT programs like PSCAT. So the most basic example I can illustrate to you is a RC circuit like this, where you have, if you close the breaker, in RMS, you'll just see a switch. The voltage across the capacitor will go from 0 to 1 in an instant, okay? However, due to the dV by dt characteristic of the capacitor, you see a response like this in EMT. So that's at the very high level. This measurement is coming from a wind turbine in the UK. Here in RMS, we see, the trends are very good. It shows the general response. But then what I'd like to pay your attention to is on the steady state, everything is fine. However, when there's a fault, the system will go through transients. And these transients are extremely important for the operation of your power electronics. I'll give you one example so you understand what I mean. So you have a wind farm here connected to your collector system. There was a fault that occurred on this wind farm. This is a practical case that we measured in real life. There was a fault that took place on the wind farm, okay? If we look at the voltage against time plot, the fault takes place, okay? Fault clears, everything is fine. If you look at the RMS, you'd say, well, this looks okay, this looks perfectly fine. But if you look at the real measurements, this is a measurement that came from field, okay, the one on the bottom. Up until this point where the fault got cleared, there was a slow recovery. Now, before the system reached its tolerance threshold, where this threshold, which the controls and protection got activated, and then there was a signal to trip the wind farm. However, the same modeling in RMS was signaling that the wind farm has recovered and the fault right through has passed. So in one condition, in RMS, fault right through pass, in reality, there was a tripping of the wind farm. So this is another reason why we need to look into electromagnetic transients when we're looking at wind power electronics connected to systems which have weak grid conditions, okay? When your point of connection is weak, such as this one, it's very important to perform studies in EMT. I will spend a few minutes discussing with you what is meant by weak grids. So here is a system which is loosely based on the Australian power system. It's a very simplistic system. What we mean, and here there was a request to have a wind farm connected to a point where the condition of this point of connection is extremely weak. What do we mean by weak? Well, here's an illustration. If you inject a small reactive current or a reactive current into the point of connection, you will see a very large change in voltage, okay? Simply put, if you have a system which is weak, essentially that means your system impedance is high. So a small injection of current results in a big jump in your voltage magnitude. Another explanation of weak grids, based on our understanding of working on this for a long time, is that you have if you have many circuits connected to here, a very meshed system, then generally speaking, your point of connection is very strong. But if you have a radial one line or two transmission lines connected to a point where the short circuit level is low, if you lose one of those lines, then your system is weak, okay? So the weak grids is an indication of how meshed your system is, okay? And the second point I'd like you to take away from this is a small injection of P or Q at a weak point of connection will lead to a very large variation of voltage at the bus, okay? This just essentially illustrates what I just mentioned. When you inject a very small current into the weak point, what you'll find is the system is has unsustained oscillations. Now, this was a practical case where there was a developer who wanted to connect a solar power plant to this weak point, okay? And then when there was another line here, there's two transmission lines, and there's a transmission line here whereby this transmission line tripped. And what happened is we found that the system goes through unstable interactions. So the PV plant and the battery, okay, because they're connected in close electrical proximity, they both try to control the voltage at the common point. And essentially what happened is they started to have a hunting effect whereby they're fighting to control the voltage. And so the system had undesirable interaction. This is one form of what we call control interaction, whereby there are multiple devices in the system in close electrical proximity connected to a weak point, whereby they fight and result in such interactions. One way to fix this problem is, one, to strengthen the system through building new transmission line to make the system stronger and increasing the short circuit level at the point. Another option is to perhaps use a synchronous condenser so that you can limit the rate of rise of phase angle, okay? And essentially increase the system inertia. If you include a system synchron or a transmission line, you are able to stabilize the system. One can also say that by proper tuning of the controls, you can also achieve this. It's not always guaranteed, but it's the first port of call. And here is an illustrative example of interaction between two power electronic devices. Here on the left, we show the system had a SVC, static var compensator, and a solar farm. They were both connected in close proximity, and you see this is a very good example of a control interaction, okay? And the reasons are as we just discussed earlier. I would like to spend a few minutes to discuss inverter operation under weak grid conditions. So there's a lot of words here, and the two key points I'd like to address to you is that the voltage, especially phase angle at weak grid locations, inverters are extremely reliant upon measuring the voltage magnitude and angle at the point of connection. So maybe I perhaps explain here through an illustration rather than words. So for the inverter to operate correctly, it relies heavily on a good measurement of your voltage phase angle. Under steady state, the inverter is fine, all is good. Unfortunately, when the system conditions are going through transients, and when measuring the system condition, i.e. the voltage, the phase angle and magnitude, if the system is weak, we are unable to provide a good phase angle to the inverter. And what essentially happens is the grid following inverter struggles and may trip. So one of the major concerns is, how do we get a good measurement of your phase lock loop? How the measurement from the phase lock loop is essential, because this phase angle, in order for the converter to give a good PQ from the converter, it heavily relies upon a good measurement of V. Okay, and if your voltage measurements are like this, where your voltage measurement phase angle goes through crazy transients, okay, the PLL in the inverter has the responsibility to lock onto the phase. If this is the type of phase you've seen at the point of on the system side, then the inverter will not be able to make a good decision as to whether to inject power into the system or back off. So there is a critical importance of PLL and how accurately it's able to measure and lock onto the phase angle. So essentially what I'm saying here is, this voltage must be tracked and phase angle shift estimated accurately and fast to ensure stable response. If we're unable to do so, then we might have power reversals, or the wind farm may not correctly give the power that we want to the system. One of the most basic ways of addressing this when such situation happens is to ramp down P, and then active power, ramp it down, and then ramp Q. Okay, that's one of the most fundamental ways of doing this, but it's just a exercise, really. So what is the impact if you have a weak grid condition? Okay, so your system is weak. Okay, you have a weak grid system. You're connecting a power electronics to the weak grid. You have a fault in the system. Your converter is unable to lock onto the phase angle of the system and give a correct measurement. This is a typical thing you could find. This let's look at the fourth waveform. Okay, the fourth waveform shows the active power in blue and reactive power in green. I'd like you to pay attention to the blue trace. If you look at the overall response, you could say that actually the waveform looks good. The fault occurs it goes through some dip and then it recovers back to normal. All great. However, if you look carefully and zoom into this region, you'll see that the power actually goes in a power reversal. So this is 0 megawatt. The blue trace drops down to minus 200. This was quite difficult to explain to clients previously, but the core reason behind this is that the PLL, the angle was not measured correctly. Let's say the angle was really 30 degrees, okay, in real life, in actual measurements, but the PLL was estimating it to be, for example, say 60. This results in the power to reverse, okay? The power reverse would reject this power reversal would result in DC voltage to rise, okay? And in this case, if you have a DC chopper, and as long as it's sized correctly, then it would ride through the fault. However, if you don't have it, then the wind farm can trip. So the utilities typically don't like power reversals, and generally ask manufacturers to retune or redesign their converters to avoid this, which is under many instances very challenging. Again, I will not spend too much time on this point, but again, your system is very weak. There is a trip between this weak point and this neighboring area. Wind farm here has to produce 100 megawatts. Without any form of remedial actions, you see the system is unstable. However, by introducing a sync-on, you're able to stabilize the system. When I mentioned earlier about networks have resonance and their characteristics play a critical role, in softwares like EMT, we're able to capture the impedance of the network. So the network impedance plays an extremely important role when we're looking at performing these studies. Say, for example, you have a wind farm and you want to connect to your system, and this wind farm injects or absorbs this high frequency parallel resonance. If this parallel resonance enters the control systems of the wind farm, and it in turn amplifies this parallel resonance, it can cause problems. So it's very important to look at the network resonance and before connecting your wind farm, and perform studies to see if your devices are going to have whether these resonances play a role in the operation of the wind farm or HVDC. So far, we've discussed what is RMS versus EMT. We've highlighted weak grids, and I've explained some situations where we've seen oscillations and interactions. And based on some of these points, I'm going to now delve onto some practical cases in real life where we have seen the need for wide area modeling, okay? In Australia, 2018, there was a major blackout. I won't go through the details of the event, but the consequence of this blackout was that the operator requested to use electromagnetic transients in all their simulations going forward. And in this case, what we found is there was a particular oscillation that was seen in the system. So these type of frequencies that you can see, only a part of the system was initially modeled in EMT. And then it was found that actually you need to go further out and model Queensland and South Australia. It was only when we had to model the whole territory before it was possible to capture these type of behaviors in electromagnetic transient tools. So the need for modeling wide area systems became of paramount importance, because if you just take a small region of the system, it may not give you, it may not capture the transients that you are looking to study. I'll give you one example. We saw, and here is part of the Australian system where there are lots of power electronics connected in a meshed form, you see here. And there were some control interactions, low frequency voltage oscillations, where it was an interaction between multiple devices in this region. And this 8 hertz phenomena arised, and it was only when we were able to model a big portion of the system and using vendor level models that we could actually capture this, replicate this 8 hertz that was seen in the real life. So 8 hertz is a problem for things such as flicker, and this has to be addressed. Example 3 is a part of the southeast coast of UK, United Kingdom, where there are lots of several HVDC links connecting to neighboring countries. So the UK connects to France through HVDC links, through Belgium and Netherlands. There are multiple HVDC links. There are a number of synchronous machines that have now been displaced, but there are also a number of wind farm sites, offshore wind farm, connected through cables. There are there was a problem with voltage levels. The voltage levels had a problem in this region, and the utility was looking at installing 3 STATCOMs at Bolney, Ninfield, and another one in nearby proximity. And they wanted to see if the STATCOMs will interact with the synchronous machines and the power electronics from offshore. Okay, so these type of studies are in PSCAD or EMT programs. It's essential to perform such studies to look at control interaction and subsynchronous oscillations in weak grid conditions. We found that in order to get a good representation of the system, we initially wanted to model only a part of the system and include all the power electronics. But then we found that in order to get a correct, accurate measurement of the system, we need to go further away. So how do we know whether we should go for small system representation or very large? Depends on the study you're trying to perform. But generally speaking, most of the typical studies with control interaction and these type of phenomena, it's necessary to look at using large-scale models. Model validation is an extremely important part of the study. So when you get your data from Power Factory, PSSE, or any other format, it's very important to initially validate it between PSCAD and Power Factory. I will discuss this a bit further going forward. I will spend a few moments to discuss when we have power electronics connected to power systems, we're able to also provide system services. One type of system service I will explain is power oscillation damping. Now you can provide damping system services through your converters. This is just to illustrate one of the capabilities of PSCAD rather than a technical note. In PSCAD, we have the capability to model detailed IGBTs whereby you represent the converter down to the switching level. We have also the capability to have an equivalent circuit-based model, which still has all the sub-module representation, but you don't have to model all the sub-modules in detail. So what we would say a Thevenin equivalent circuit-based approach. So MMCs, all forms of converters can be modeled down to the switching level. Here, as an example, what we're showing is that, yes, we've modeled the MMC, but what I'm interested to show you is that when we have weak grid conditions, we may need to allow these converters to provide system services. So one option could be to modulate. For an MMC, for example, you have the ability to modulate active and reactive power independent of each other at both sides of the converter. Sorry, in one side PQ and the other one VDCQ. Okay, so you have three control freedoms. Okay, P, Q, and Q. All right. So in this example, I'm just illustrating a very simple case where I'm going to modulate the active power of a HVDC link in order for the system oscillations to damp. So here we take a very simple case, a contour-based system, connect an MMC in parallel. So 400 megawatt flows through the AC tie line, 200 megawatt flows through the HVDC line. We're going to take measurements from the system, and this phase angle is going to go through a power oscillation damping controller, and that's going to modulate your HVDC. There is a fault that happens on the remote end, bus 9. Without any power oscillation damping control, we see that the system has a poorly damped mode. And by modulating the HVDC, DC link power, you see the power of the HVDC in nominal condition was 200 megawatt. And then it gets modulated by 20% overhead, okay, for a short period of time. This modulation effect allows your power oscillations to stabilize. So these are typical things that you can perform in PSCAD. You can provide system services. You can look at also the voltage across the converter arms. You can see what is the voltage across one of the converter arms as well as cells, and whether they are fully operational. Okay. So I now move on to the last part of our presentation. I'll spend about 10 minutes on this, and then I'll go through some example cases. So MHI has developed a tool called PRSIM. It's a power system import tool, which allows you to take data from various tools such as PSSE and Power Factory, and then develop that model and bring it into PSCAD. So you can take information from PSSE or XML format, DGS 6.0, and then through a process, you can bring into PSCAD. The general process is such that you create your PRSIM case, you import your power flow data, you expand the area of interest that you want to study, then you would export the network into PSCAD, and then you can perform your simulation. I want to illustrate as an example. This is a practical project we're working on with a client. Here we are, I'm showing you that the capabilities of not just building, small systems, but you can develop the full utility scale. This is the left diagram here shows a single line diagram of the network. It's around, it's tens of thousands of buses. And then we can, and this model on the left shows the exact thing in PSCAD. So this is a PSCAD case. It's been redrawn to mimic the single line diagram, but it's a PSCAD case of the system. And here you see network equivalence. I will discuss this in further detail. Now, when you have very large systems, you have to sectionalize it, and I will explain that in a bit. So if we go inside one of these modules, like one of these substations, what you see inside the substation is your detailed representation. You have your buses, transformers, loads, your generators. So you can model very deep down to distribution network if you really want to. Whether that's necessary, that's a decision the engineer has to make. So as I mentioned, sometimes you don't want to model like here, as you can see, the boundary here, STWB, there are 4 connection points with the rest of the grid. Here we don't want to represent the rest of the grid. So here we want to equivalence. We keep all this area, but at this point we want to perform a network equivalent. Okay, 1, 2, 3, 4, 5, 6 equivalent points. So here we can, PRSIM has the capability to automatically generate the network equivalent, which is essentially source impedances. The network equivalent source impedances are derived through matrix reduction technique, where the entire system nodal admittance matrix is reduced with only the buses in the study area and the boundary explicitly retained. So anything these sources and this representation would consider the power flow, the power flow condition, and the short circuit level at that point whereby you equivalenced. So if you have a utility large scale system, our recommendation is not to build everything in one case, but to build them in small parts like this. So I have a larger case. I've split the case into 8 different projects, whereby each project has been validated individually. Once it's validated, again for power flow and short circuit levels, then we would interface them through what we call electrical network interface or parallel network interface, PNI, whereby you use a line to connect. Now, this line would be a real line. It's just split to connect the 2 systems. I'll discuss this further on. Once you've built your case in EMT and you've sectionalized it through parallel processing and parallel cases, then the next step would be to perform power flow. In this case, I'm looking at 4 different branches, branch A, B, C, D. We find power factory gives 222. In PSCAD, we're getting 224. Here, I purposely included this to show that you may find cases where there are outliers. They can come as a consequence of many reasons. It could be that the model that you use to import from Power Factory, some components, some details are not representative. It could mean that you need to model the line in more detail. It could mean many things. But generally speaking, I have seen very good match between Power Factory and PSCAD when imported through raw file. I haven't extensively tested Dick Silent direct import, but I have worked with many clients who are doing this process and seeing very good results. When you design your system, my recommendation is to build your system AC system only. You can also use PR sim to bring in power electronics. You can ask. So here is a case in Power Factory. If you're going to test your generator model, my recommendation is to first create a single machine infinite bus setup where you take one generator only with all its controls, and then connect it to a SMIP case, single machine infinite bus, and then use a PRSIM conversion tool to achieve something like this, a network equivalent, and then run and see if your generators match against PSCAD. Here is an example where the generator has excitation control and PSS, which are not standard blocks. They're not IEEE standard models. Here, under such situations, you have to develop your controllers block by block. So these controls that I'm showing you here, they've had to be built manually according to the data sheet. Once we do building the excitation control, then you can apply a fault in the SMIP case, apply a fault to the bus, and look at the behavior. Do the power flows match reactive power? In this case, it matches well. And so we are happy. And then we can say, okay, now we can integrate this synchronous machine into our system. For the projects I generally do for my clients, I always create a SMIP case, test them individually. If I'm happy, then I connect the synchronous machine and its controls to the power grid. Another important point is when you are integrating power electronics to the system. So here I'm showing a wind farm, type 3 wind farm, that is going to be connected to my network, okay? These wind farms, if you remember from the slide, let me just go back. If you remember from the slide, they take some time for them to reach steady state, right? So they will go through ramp up. To get to the steady state, this started at 13. But if you look at the waveforms from t equals 0, you see they'll take about 3 to 4 seconds for them to reach their steady state power. Okay, there are some blocking for HVDC. There's blocking, deblocking for wind farms. They require some time for them to reach the power set point they are requested, few seconds. So what we generally do is first the network will see the network will first see a voltage source which has the same conditions as the wind farm. So this is disconnected. This path is not seen by the network up until T release. So up until T release, for example, at 5 seconds, the system initializes with a source. And then at T equals, say, 5 seconds, the source disconnects and it will be the wind farm and all its controls, which have been fully energized and initialized, that will be connected to the grid. So this is one type of method that is adopted now more in industry for studies. This means that for the first few seconds, you don't see a lot of transients in your system, but you have more of a smooth operation. When you've designed your, here this shows a part of the network developed in PSCAD of a utility scale network. We can then apply fault strip circuits and compare them with field measurements or against the software that you use to import the data. Here, generally speaking, we apply faults, look at measurements, and compare it against known data. But once you have a validated system, then you have the freedom to integrate your power electronics controls, your FACS, your HVDC, using a logic like this, ideally, and then perform many system studies. So with that, I end my main discussions, and I will have 2 more final slides regarding modeling of the Chile grid. But before that, I would like to give you a moment to take a break and we will discuss how do we import models from Power Factory and PSSE into PSCAD. I'm going to illustrate the PRSIM tool. I'm going to begin by using an example from 14 machine bus example from IEEE 14 bus that I use from the example library. The steps are very straightforward. I'm going to initially show you how to develop this through raw import. So Dix Island has two export options that PRSIM accepts. The first option is to go to export PSSE. So long as you have the export PSSE toolbox, I think these are additional licenses. You can, step number one would be to run the load flow. So we'll do that together. Run the load flow, then go to File, Export, PSSE. Then we need to specify the name. So I'm going to call it 14 bus example. I'm going to save it on my desktop. We can also specify the same thing as a DYR, because this might have dynamic models. You see, there are some synchronous machine models. So we want to introduce their dynamic models, like the dynamic characteristics, if they have AVRs and so forth. Make sure you choose version 33. I will leave this as an automatic option and then press execute. You will see that we have now successfully exported the raw file and DYR to my desktop. Then PRSIM was designed so that it mimics a similar design to PSCAD. So if you open the software, you see that the interface looks very much similar. We have all the master library components. We also have what we call a PRSIM interface library. I will discuss this in a moment after we've built the case. So in order to build a network, the step number one is to go to File, go to New, and then I'm going to create a new case called 14 bus example. 14 bus example. I'm going to create a new case. Let me just do it this way, 14 bus. New. I'll just create a new case for the moment. The next step, once we've created a case, is to import the raw data, or we can have the option of importing directly from Power Factory. Now, I understand for the Chilean grid, because the usage is Power Factory, this is more of a preferential. So I will illustrate both. I will start with the raw. So import raw file. The data did come from Power Factory, but it's just another way of exporting. Once we've exported, this side and this side will give us an overview of the system. It's an extremely small system. It's just illustrative. And then what we can do is expand bus. If you come to expand bus, you see that it gives you this option. So I can say I want to start with bus number 8, and then you'll see a plus sign here. So if you click this, it goes to the next bus, and you can keep expanding further out until you have fully developed the case. You may be required to do some moving around because we don't provide, if you have the log file, loc.log file, which is a PSSE file, then it will also know the coordination of all your elements. Since I don't have the log file, I have to manually move this until I get the topology that I want. So you can just move things around. And as an example, here, if you keep pressing the plus button, you see the plus option has now gone. This plus sign here indicates that there is more elements connected to this point, okay? So if you don't want to study further away, we can just leave this here. This might be the point where we want to stop. We don't want to expand any further away. So wherever you see a plus sign, so there's a plus sign here, there are more elements you can see here. I'm going to illustrate how the software will just automatically create a network equivalent for us. So if I press export network, here it asks you, do you want to include the network equivalence? I say yes. Do you want to include dynamics? I can say yes. But if I specify yes, you have to tell the software which models you want it to have a dynamic model. I will illustrate that in a bit. So now you have your PSCAD case. Here you see the two locations where we decided to do a NetEQ, where it created a sticky note around it. Okay, this means that there's a network equivalent at this bus. Now at the top, you see a NetEQ. There's two connection points, bus 5 and bus 2. So if I go inside it, you see that this source includes the characteristics of that point, the power flow, the voltage, the short circuit level, everything is contained within this source. So you don't have to model further away. So this is one option, is to just model, take a large network data, expand only the area that you're interested in, and then let NetEQ take care of it. If I want to now include these generators, because if you refer to the data, there was a synchronous machine connected here, another one connected here. So let's include these synchronous machine models. So all we have to do is come here, double click on the element, and then specify that I want you to replace this model with all the following options. You have a large array. You can also include your own library here. For example, if this was a wind farm and this is a vendor level model, you can load your own custom library and then say to the software, hey, I want you to replace this voltage source with a wind farm according to the model, according to the link that I give you. So that's what we call a substitution. In this case, maybe I'll convert this to a synchronous machine model. I will keep the machine excitation control empty, but I wanted to include the converters. That's one. And let's say the same for this one. And then we'll say export. I'm going to include network dynamics. This time I will fully expand the system, so there is no NetEQ. It doesn't look very pretty here, but that's not the point of the exercise. So export, NetEQ no longer needed. I can represent my lines as compact, that's fine, and then include dynamics. Now we'll get another case where this time there is no NetEQ. As you can see, your whole network has been represented. And this time you have your source represented as a synchronous machine, which has your excitation and your governor and PSS. Of course, you have to specify these models. But the key point is all your generator characteristics are included in the generator data as well. So if you look at the generator data in Power Factory, if you come and look at the H constants and all the transient time constants, so forth, you'll see they have been correctly inputted in this field. So you can bring in synchronous machines, you can bring your whole network, you can also bring in more advanced things like asynchronous machine models, so that's like a wind farm, and so forth. You can bring in your own library. You can have HVDC links. You can replace these things. My personal experience is that it's always better to first build the network. Just focus on building the network, getting the machine models developed as a single machine, infinite bus, as I illustrated from my PowerPoint, integrating them once you're happy that they are correctly operating in a simple scenario, once you have your network developed in PSCAD, then you can add your wind farm, your power electronics using a logic as I've illustrated here. I wouldn't rely heavily on PRSIM to, take a voltage source and replace it by wind farm. So now this is an illustration of how we did it for a raw file. We can equally do the exact same thing for exporting through direct. So you don't need to have PSSE. So I can convert this case from Power Factory directly to PSCAD using this option called DGS format. DGS format will take, you have to say version 6, it's an XML file, and then you specify the name, 14bus.xml. It's extremely important if you're going to do this exercise to connect the variable set. What is the variable set? All you have to do is go to the root of PRSIM, wherever your PRSIM is installed. In my case, my PRSIM is installed in program files, PRSIM, beta. We have included the file called DGS export definition v110. You have to make sure that you import this. So I will do that. Import PFD. I will go to the root file here. It's already there, but for illustration, I'm going to do it. So this file here, once I go to the root of my PRSIM, I will simply execute it. Okay, so that now is included in my definitions. Okay, I can delete this one. So all the elements that PRSIM requires to read are included here. So if you're going to export this directly, the steps are export, DGS, version 6, XML, and then make sure this is linked, and then simply execute. And now we have successfully exported this case to my desktop. It's called 14bus.xml. Again, we can go back to PRSIM, file, create a new case. Then right-click on this case. This time we're going to say import Power Factory XML. Go to the root file. Now the latest version gives you a few options, whether you want to import substations as page modules or just no. I'll just say no for now. You can play around with it. And then again, just like before, you'll see the data getting imported. There's no errors. And you can also click the option here called expand all. Expand all will bring it in. You see it's done quite a tidy job with the XML option. It's done a very clean. I guess some coordinate information is provided, perhaps. So I can then press export network. Here I'm going to say, yeah, sure, include dynamics. I generally don't include dynamics because I like to be sure that the generator models I'm building are accurate, and then I manually include it. But for an illustration, I will include it. And then that's it. That's all it takes. Once you have your PSCAD case, this is still in PRSIM. You can then go here and launch PSCAD. And then you can you will see the case developed. Okay. So then, of course, you have to validate this for power flows, short circuit, run tests, make sure everything is okay. But that's the gist of it. And we, for this webinar, we took part of which is my final 2 slides. We took part of the network in Chile, one area as illustrated in Chile, and Gabriel, you can discuss this a bit more detail than I can. And we developed the case in PSCAD using this PRSIM import. Once we develop this case, we then check the power flow, and you can see that the power flow matches very, very well. I've just shown an illustration of 4 cases, but I have an Excel sheet that shows all the lines, and the match is exceptionally good. So it's possible to develop the full Chile grid, just like we've done with other models, cases like here, in PSCAD. And this is showing the system. This is showing the part of the Chile system in PSCAD. And it's been, arranged to look like the Power Factory case or the single line, but you can further enhance this. So you can go inside the substations and see the details. It's not well presented, but it can be further polished. So as an example, what we can do here, for example, is note that the whole system currently has voltage sources. There is no synchronous machines. And we never study, I don't recommend performing studies where you have many voltage sources in the system, because these are fictitious elements. So, but as a test, what I can do is I can add a multimeter in these locations. I can specify that I want to measure, let's say I want to measure the power P1 and power flow P1 and Q1 flowing through this path, this line, during a fault condition. We can do that. So we can say, let's plot the signal. Let's do new, add overlay, so we have Q as well. And then I can run the system. This might take a few minutes. And you will ask me probably questions. How long does it take to simulate a large system model? Can I use a laptop? Do I need to use a high performance computer? So you can see the simulation is exceptionally fast. And don't forget, we have built this system, this Chile system, part of it all on one project file. If we had split this into different areas, this will become much, much, much faster. So one idea is to split it into parts and connect it through PNI. But you can see the system simulation is pretty fast already. My fault takes place at 5 seconds. Perhaps 2 seconds would have been sufficient. But you can see that you can run large scale systems, and it runs pretty fast. So I will let this run. It'll take 2 to 3 minutes, and I guess we can. Gabriel, if you have any discussions to add while this runs, please come in.
Joseph, thank you very much for such a nice and comprehensive presentation. Actually, we got a number of questions beforehand, and I'm going to select a few ones because I know that you have something else to do, and you have already gone for more than 1 hour, so I don't want to take much of your time. One of the questions is, what kind of computational infrastructure is needed to perform EMT studies at the system level? Mm-hmm. And the same is, how do you initialize the simulations? And if there are also other techniques like dynamic phasors? Okay, sure. So let me discuss computation and what hardware is necessary. If you you see that, like, if I run this on my laptop, it will run much slower than this. But if you have no choice but to use a laptop, the way PSCAD works is that if you have an 8-core machine, PSCAD software takes 1 core, and then it has 7 more cores left. So long as you have 7 cases in your project, what it would do is each core will be assigned to 1 project. So if you have, for example, in this case, I have an 8 cases, and if I have an 8-core system, then almost each case will be allocated to,
each project, okay? But if I have a 4-core system and I have 8 cases, then 2 cases will have to share the memory of each core, and that will significantly drop the speed. Now, if you have 30 or 40 cases, like a case like this one, whereby I have many cases that I'm running, okay? If I have a case where it's 15, then each core will take 1, 2, 3. This is a 14 core. If I have a 4-core system or an 8-core system, you'll struggle. So for that reason, we recommend using 64-core systems, or like high performance computing with hyper-threading. So computation is important. The way parallel PNI is important, splitting the case into smaller parts. Having wind farms built on, here's another case where I can show you, where we have wind farm models. We have power electronics in the form of HVDCs, STATCOMs, a lot of power electronics essentially connected here. So you have HVDC, wind, we have STATCOMs, SVCs. Here, for such scenarios, you need to have a high-performance computer. It just simply won't work.
Yep. Okay. So it's a matter of high-performance computing, and also the possibility of parallelizing the algorithms, which is something that is inbuilt in PSCAD.
Yeah. Yes.
Okay. Is it possible to automate the system implemented in EMT? I guess the simulations and the runs. I mean, can you use a sort of a script?
Yes. So most of the works we carry out involve scripting. So for example, here you see on the left side, you can read a Python. You can automate your actions through Python, load a Python file, and run scripts. So when I perform system studies, I don't generally like apply a fault and then wait. I write a code in Python and ask it to run 10 different faults. I specify the fault locations, and the script will just pick up, and then it can take those information and pass it to a output file. But there's ways to automate your system. One option is to use the automation of Python.
I see. Perfect. Thank you. This is a good one, I could say. When performing system studies, or I could call it the EMT studies, how far from the irrelevant bus bar we need to go in modeling? I mean, you touch it on that, but maybe it's worth to repeat that.
That's a very good question, and again, that generally depends on what type of study you're performing. If you're performing, say, a switching study or a TOV, TRV type study, then generally 3 buses away is sufficient from the point of interest where you're trying to study. If you're performing some wind integration studies, or looking at looking at frequency or different types of control interaction, we generally see that you really need to go further and further away, like we have here as an example, right? So it's important to look at what study you're performing, and on that basis, then decide. Okay,
thank you. The last two is PRSIM included in PSCAD licensing package, or is it completely standalone software?
We have PRSIM Pro Enhanced, which comes included with PRSIM, and then PRSIM has two licensing. One is PSSE only. One is Power Factory, or you can request for both. So yeah, if you drop us an email, we are happy to send you a trial license to try it out. And then yes, that should be. If you drop me an email, or Gabrielle, I think Gabrielle, they have your email, they have my email as well. We can set you up with a free trial license.
Absolutely, we can help them. I could say that's the last one. Otherwise, it's going to take 1.5 hours for you, and I know you have something else to do also. So
don't worry about it. It's okay.
Then let me one more. Okay, then if you still have the time, you went through this one, but it may be good to repeat it. I would appreciate showing a case where you can take a reduced model of the network in this silent power factory. This is because this program is the one that is used by the National Electric Coordinator for its simulation in Chile.
Yes. So yeah, I mean, I can tell you one thing. There are a few utilities that I'm in discussion with that they also have Power Factory as their network model. Actually, this case that I'm illustrating here, this large-scale network that I illustrated here, the data was in Power Factory. So this network data, all of it is about 25,000 buses, if not more, is in Power Factory, and we've developed and validated it again in PSCAD. So you saw the fault levels and short circuit levels matching very well between the two tools. And to just the key point to remember when you're developing your case, make sure you are using, when you're exporting the case, it has to be, you select DGS, make sure you select version 6, XML, link the variable set, and simply export. Yep. That's pretty. If you have trouble, do send us an email. We have a very good support team, and they will help you with telling you what the problem is if you're having.
Good point.